Okay, so the second half of section 44B on page 182 and 183, quite different from what we did yesterday. Got a little bit of the things that are the same, but the main core concept here is a factor theorem, and if we take, this is what factor theorem is about, if we use just regular straight up numbers. If, for example, I wanted to take 8 into 328, you know the process. We went over this before, but we'll do it again. What's the first thing we got to ask ourselves? How many times does 8 go into 32, and how many times? 4. And then we take that, whatever we decided there, we take that times that and write it here, right? We get 32, and then we change the signs and add. That's how we've been taught to think about it, right? So we get 0. Bring down the next one, which is 8. Does 8 go into 8?
Yeah.
How many times?
1.
1, and then we take this times this, and we get 8. And we change the signs and add, and we get a big fat 0. Because we got a remainder of 0, it means that 8 goes into 328 evenly. That's one way to say it. But here's a better way that refers to what we're going to be doing today. Because the remainder was 0, 8 is a factor of 328. And so is 41. Because the remainder was 0. In other words, because the remainder was 0, we can say 8 times 41 is 328. We know that from what we discovered here by doing it longhand. Yeah? What we divided by and what we got as a product equals what we divided. Yeah? That makes good sense, right? Because the remainder was 0. If the remainder were anything but 0, then we would say 8 is not a factor of this. And 41 is not a factor of it. The example of that might be something like 28 into 296. That goes in once. There's 28. Change the signs and add. I get a 16. 16 is too small for 28 to go into, so we get 1. And because the remainder was not 0, 28 does not go into this evenly. Nor is the thing we got a factor of it, because the remainder wasn't 0. But we can say it's, as we learned before, it's 16 over 28, which we would reduce to 4 over 7, 1 4/7. But what we've discovered, the main thing I'm trying to emphasize here is because we got a remainder other than 0, you can be certain that 28 is not a factor of 296. Does that make good sense? You understand the decision? That's the factor theorem. And if that was easy for you, then that's great. That's how it applies to numbers. Now we're going to apply it to polynomials. It's not very hard. And it says right there in the core concept, it's a very easy statement. It says, a polynomial function has a factor called x minus k if and only if you get a remainder of 0 when you evaluate it. Okay? So, in example 5, it says, determine whether x minus 2 is a factor of that cubed polynomial. Also, B part, a whole different problem. See if x plus 5 is a factor of this polynomial. So all we have to do is decide yes or no. If it were these two we were doing, we would say yes, and that's when we would say no, because of the value of the remainder. Okay. So let's do it with a polynomial, see if we can answer the same question. It's pretty easy, really. Notice that the thing that we're trying to decide is a factor or not, in both cases for A and B of this problem, example 5, both of the things we're trying to determine are factors are linear, which means synthetic division is a good choice because it's quicker. So if I were going to do the A part, what would I put in the box? 2, because we're trying to decide if x minus 2 is a factor. Do you understand why the choice of 2 for the box? Everybody clear? Okay, then I would look at f of x and see if all of the, oh, I thought it was a cubed one, is it? All of the terms are there. We've got a squared term, a single term, and a constant. So they're all there. I don't have any zeros to build in. And I've got a 1, 2, negative 4. 1, 2, negative 4. So we do the synthetic. We got 1. 1 times 2 is 2. 2 plus 2 is 4. 2 times 4 is 8. 8 negative 4 is 4. This is where the remainder should go. So the answer is a big fat no, because we got a remainder other than 0. See the decision? This thing at the end is always the remainder. I always box it up just to separate it from the others because it's a little different from what we get. So that is not. Now, to do the next one, what would we put in the box to do the B part? This was A.
-5.
Yeah. Okay, -5 in the box. Is there anyone who does not understand that choice? Then we look at the polynomial. It's a 4th degree, and I've got a 4, 3, 2, but I'm missing a 1. Make sure you build a 0 in where it goes. So we're missing the linear term. So my coefficients are going to be 3, 15, -1, 0, and 25.
Why is there a 0?
Look at it. You tell me. Look at the powers. The powers march on down from 4, 3, 2, and there's not a 1, 1. Got to build it in. Do you understand that? Watch for that. It doesn't happen very often, but you have to watch for it every time. Because if you had not built that in, your answer would be no on this one. It actually turns out to be yes. You've got to have that where to hold its place. So we bring a 3 down. Have -15. Oh, that's a cool thing. 0, 0, -1, +5, 5, -25. Big fat goose egg tells us yes. And this is, because we decided yes, this is a factor of this. This is what we can write. You got to understand what we have here. We can write this now. We know for sure that x plus 5 times this result. Remember, this was a 4th degree polynomial? Then the result here is a 3rd degree. So this factor right here that we put in the box here times this result, that's like saying 8 times 41, times this result, which is 3x cubed plus 0x squared minus x plus 5 equals this thing. I don't have enough room, so I'm going to just stack it up. This times this equals this, and this was what we divided by. This was the result that we got, and that product is what we started with because the remainder was 0. Do you see that or not really?
I don't see that. I don't know where you got that 5 from. When you went -15.
Then you need to stay with me. I asked everybody if you understood where it came from. You say a word. Look at part B of page 182, example 5. Are you looking at it? Part B. It says, decide if x plus 5 is a factor. That's the thing we're going to be dividing by. What do you put in the box? The thing that makes it 0, -5. That make sense or not? Have you done the synthetic division assignment?
I did not.
That's your problem. If you haven't practiced it, you don't know what I'm talking about. You need to get that one done before you tackle this one. It's dependent. You need to know how to handle synthetic division before you can start making other decisions with it. Okay. Everybody okay on example 5, at least to this point? Yeah? No? So we decided no on this one, and there was nothing more to do. But we decided yes on this one, and I just wanted to show you what it means. Since we decided yes, because that was a 0, it means that that factor times the result that we got to what we started with. That's what we did with the 8 and the 41. You see how it correlates? I hope. Okay, now this is how we're going to use it. Once we figure out whether something actually is a factor or not, we have to continue. Kind of like yesterday. You factored something, and if what remained had a difference of 2 squares, you continued to factor. That's what synthetic division is all about, people. Whether you realize that's where we're headed or not, I'm telling you. Synthetic division is all about depressing. It's not depressing. But you depress something from a 4th to a cube. You may use it again to depress a cube to a quadratic. And then you use quadratic skills to depress it even further and get all of the factors. So this is a method of factoring. It's kind of weird, but we've determined that we have a factor and a depressed power factor. So then we may be able to use some other skill to factor this. Oh, we can't. This is a factor further. But it's a method of factoring. We get your factors listed until it's completely factored all the way down. And you will see why that's useful later. I'm only teaching you the skill. How do we factor something that has a higher power than 2? Well, you do it with synthetic division. Keep busting it down and depressing it into a smaller and smaller powered polynomial. So this next one actually asks us to do that. It says, show that x plus 3 is a factor of this 4th degree polynomial, and then finish factoring it completely. So we're supposed to show that x plus 3 is a factor, which means we expect the remainder to be 0 because they're asking us to show it. It means they already believe it. We just have to establish it. So because it's x plus 3 that's going in, we choose -3 for in the box, and we've got a 4, 3. We're missing the square one. So we have a 1, 3, 0, -1, -3. Please speak up now if you don't understand why I wrote what I did here based on that problem. Okay, so we carry out the synthetic, bring down the 1. -3 times 1 is -3. Oh, get big fat 0 there. -3 times 0 is 0. 0 and 0 is 0. -3 times 0 is 0. -1 and 0 is -1. And -3 times -1 is actually +3. So we did show that it's a factor because we got a remainder of 0 right there. So this is what we've got so far, folks. We've got x plus 3 times, remember this was a 4th degree? This is a cube then. So it'll be x cubed squared, single, -1. So far, that's what this 4th degree polynomial has factored into. This linear, because that's what we put in here, times this. And then you look at that, just like you did yesterday, and you ask, could I factor that further?
I guess you just put it here.
Can you factor this one further? No, it's linear. It's got a coefficient of 1 here. I mean, an exponent of 1. Can you factor that one further? As what? What do we call it? What do you call this?
Oh, a difference.
Difference of
Square. Cube.
cubes. Well, this is a cube. That's the only thing it can be. This can't be a square. So we continue factoring this as a difference of cubes. That was the thing I asked you to memorize as you practiced it yesterday. Does anybody remember how this one will factor? What goes here?
X squared.
Nope.
X.
Nice try. X
The next one will be x squared.
-1, because this is 1 cubed. Remember, when you factor cubes, you take one of each, you cube it that, put it here, you cube it that, put it here. And then you build the next part, which is a trinomial out of this. What goes here? What goes here? X squared plus, good, plus x plus 1. And then we've got this factor up here. And I promised you that this would never factor. So this 4th degree polynomial we started with, which was where these coefficients came from, this 4th degree polynomial has these 3 things for factors. Not only that, for your information, this 4th degree polynomial will cross the x-axis twice. Because remember I told you that in this situation of cubes, this trinomial will never factor. Furthermore, its zeros are always imaginary. So this is only going to cross the x-axis twice, once at -3 and once at 1. So we have found the zeros, the real zeros of this polynomial. We could find the imaginary zeros if we applied the quadratic formula to this, but I'm not interested in those. What I'm saying is, you started out with a 4th degree polynomial. It's got a positive leading coefficient, which means it should start high and end low. Do you agree? Yeah? So this graph, without even ever graphing it, looks like one of 2 things. It's got a 0 at -3 and a 0 at 1. And that means that it starts high, hits here, comes back, and maybe it comes around like this and goes up, never hitting again. Or perhaps it does that little whippy thing first, like this, and then hits at 3, -3, and then at 1. One of those 2 things, because it's got to start high and end high, the 4th degree. And it has only 2 real zeros, because these 2 always produce imaginaries. There's a lot of information here. That's what we're trying to get at by factoring the thing. You look at the factors, and if you remember what you've learned so far, you can determine a lot of stuff about it. Anyway, this is factored completely, and that's what we're practicing today, is just getting it factored as far as possible. The rest of the chapter is about making the conclusions I just alluded to here. One more example. This is a real-life example. Have any of you ever ridden a roller coaster that goes underground?
Yeah.
Was it dark inside, the underground part? Pretty scary, huh? I think. I've never ridden one that goes down underground. However, I have been down to Downetta. Anybody been down to Downetta Hot Springs?
Water slide?
Yeah. They call it the black hole. And it shoots you down hard and fast. And somewhere underground where it's totally pitch black, it turns an entire 180 degrees to bring you back out so you can go ride it again. But you never know where it's coming. So your body's just going down fast. You get flipped around and come out the other end and back into the light. It's pretty awesome. But it is pitch black in there. Anyway, that has nothing to do with the problem. So here's our situation. We've got a roller coaster that part of the ride is underground. And they've got a graph of it. It says during the first 5 seconds of a roller coaster ride, the function h of t, they call it h of t instead of f of x, because it is the height as a function of time. The height of the roller coaster above ground is a function of time. Is equal to this cubed polynomial. And it represents the height in feet of the roller coaster after t seconds. The question is, how long is the roller coaster at or below ground level in these first 5 seconds? Can you see from the graph where it occurs? See where it goes underground?
Yeah.
That little piece that's to the left of the y-axis is irrelevant because we start the clock when the ride drops for the first time. You with me there? Okay. So it goes underground somewhere between 2 and 5. It's fairly clear from the graph that it crosses the x-axis at 2. It's not so clear where it crosses the x-axis again, but it is a little bit after 4. Are you looking at the graph? Can you see these conclusions? So what I have here, folks, listen carefully to how you use this in a real-life situation. You have a cubed polynomial, and you have one of its zeros. 2. You also have another one of its zeros if you want to use it. -1. It's irrelevant to the roller coaster ride, but from the math point of view, -1 is also a root, it looks like, doesn't it? Which one should we put in the box? Because it's zeros that go in the box. Remember, I told you this one has a 0 at -3. Well, that was one of the zeros that was in the box. You could put a 2 in the box. You could also put -1. Which one should it be? Either one. They're both zeros. It doesn't matter which one you put in the box. But I'm going to show you something. I'm going to show you 2 ways to do this, and you can decide what you like. Please try to get a handle in your mind on both ways so that you can make a proper decision, make your life easier when it comes down to it. So here's the thing. They were talking about the zeros of the graph, like I talked about just a minute ago, when that thing came down and hit -3 and then hit 1 and never hit again. Talking about zeros of the graph, because that's what we have a picture of. And notice that they never said anywhere in the problem, show that this factor is a factor, as this thing. Show that it is, they don't give you anything to divide by. You have to get the thing that goes in the box from the graph. And there are 3 real zeros on that graph. 2 of them are clearly identifiable. The third one there, just a little bit past 4, is not. So you don't want to use that one. But which of the other 2 do you use? It doesn't matter. You want to use a 2? We can use a 2. So I'm going to put 2 in the box. What are the coefficients of the cubed polynomial we wish to depress?
4, -0.
I don't think I'm going to depend on you guys.
It's 4, -25, 34.
It's 4, -21, 9, 34.
That's for -1. We're doing 2.
It's still the same polynomial. Yeah. It's the height polynomial that's in the middle of the problem.
Why is it different down there?
What? It's different in your book?
Yeah.
Really? Sometimes they print the teacher's edition different than the student's edition. No, it's just what I said. 4, -21, 9, 34. Where are you looking?
I'm looking down there.
Well, why? Look up here. That's what I'm dividing. That's the height polynomial. And we wish to depress that from a cube to a quadratic. Okay? So if you're looking at the actual polynomial presented in the words of example 7, we have a 4, negative 21, 9, 34. That's what we wish to depress from a cube to a quadratic. And we're going to use one of the zeros that we can clearly see. A crossing of the x-axis, that's a 0, is 2. We could have also used negative 1 in the box. Do you see that from the graph? Are you all caught up with these ideas and why we're deciding this and this?
Yeah.
Anybody else questions? Okay, so we do our synthetic division. Bring down the 4. I get an 8 in that product. What's negative 21 and 8? Good. What's 13 times 2?
26.
So it's negative 26. And negative 26 and 9 is?
Negative 15.
Negative what?
15.
What's 26 minus 10?
Negative 7.
Oh,
Negative.
Negative 7.
Negative 17. 2 times 17 is what?
34.
34. And that's negative. So I get a big fat 0. That was good. Now from here we have two choices. I told you I'd show you 2 ways to do this. You have to decide which way you want to do it. What I have now, I have shown that x minus 2 is a factor. We knew it would be because it crosses 2 on the graph. What remains, this was cubed, what remains is 4x squared minus 13x minus 17. That's a quadratic, and I wish to find the zeros of this so that I can find, what I'm really looking for, folks, is all 3 zeros of this graph. I know one of them's at 2. I can find the other 2 of them by factoring this, or doing something quadratic on this to find the other 2. So at this stage right here, you have 3 choices. You could graph this. It won't show up like that graph because that was a cube. But you could graph this and find its zeros. That's one option. You could factor it if it will. That's another option. Or you could quadratic formula it. That's another option. What would you like to do?
No.
I heard that first, quadratic formula. So we go. X equals the opposite of b, 13, plus or minus the square root of 13 squared, 169, minus 4 times AC, that's 4 times 17 is 68. Yeah.
Yeah.
Over twice a. So what is 4 times 68? That's the first thing you got to do is take 4 times 68. It'll be positive because it's a negative times a negative.
156.
272.
At least a couple of you need to agree. 4 times 68. 272?
Like 4 again, though.
What?
Isn't it 4
Well,
8?
she already times the 4 and the 7
Oh, yeah.
together. And there's
Yeah, I took 4 times 17 stuck it here. Now I'm ready to take 4 times 68. 272, is that right?
Yeah.
Now add 169 to that.
441.
441 over 8. Okay, that's a pretty large number. We're going to have to figure out if that's a perfect square, and if it's not, we're going to have to prime factor it. Is 441 a perfect square? Of 21, right? Okay, so that's nice because that gives us plus or minus 21 over 8. What is 13 plus 21? 34. And 34 over 8 doesn't reduce exactly. But how many times does 8 go into 34? 4. How many left over?
2.
2 over 8 is?
1/4.
1/4. Guess what? That's where it crosses the x-axis over there where you can tell exactly. What's the other one? What's 13 minus 21? Negative 8. And what's negative 8 over 8? Negative 1. That's the other place it hit the other x-axis. Now let me show you what I think of as a better way in this situation.
Okay.
And that is to start the problem like this. Just like we did, choose either 2 or negative 1. I'll choose the 2 again, since we've already done the arithmetic. So you're starting this out, and you're trying to figure out the factors of it. 9, 34, and we run that through. Put put a 4 down here, we get -8 or +8 and -13 and -26 and -17 and -34, and that's a big fat 0. And then you can take the other 0 you observed, which was what? What's the other 0 you can tell for sure? -1, and put it here and do it again. In what remains here, you can do it again. We bring down the 4, we get -1 times 4 is -4. -4, -13 is -17. And -1 times -17 is 17. Get a big fat 0 again. We expected that because -1 was a 0. What do we have left? This was a cube. This was squared. This is linear. We have 4x minus 17 equals 0. It's an easy thing to solve. 4x equals 17. X equals 4 1/4. I find that easier than that. Yes,
So you just plug it into your calculator and the y equals, and then find the 0.
absolutely. But there will be others where that's not going to be your best bet. There will be others where the only 0, like you might have a cubed polynomial like this, and you might have 1 0, which you can graph and find, or you take their graph and use it or whatever. But the other 2 are obscure, they're weird, they cross in different places or whatever. And then when you get to here, you have no choice but to do this. And the 2 things you're going to get are going to be weird. But because there were 2 very clear 0s, we could use this method. You could also ask your calculator. Now, if that had turned out to be something like 4.267897437, something like that in your calculator, which is not a nice, neat number like 4 1/4. If it turned out to be something irrational like that, then you better get to here because we're going to want an irrational answer. You see what I mean? So there are reasons to do this. But if your calculator gives you 3 nice, clean answers that are rational, then write them down and move on. Okay? All right. So a couple of ways to find that third 0. But we still haven't answered the question, which was what? What was the question we were supposed to answer?
How long is it below ground?
How long was it below ground? When did it go below ground?
2.
At 2 seconds. When did it come back up?
4 1/4.
4 1/4. How long was it underground?
2 1/4.
2 1/4. 2.25 seconds it was underground. Do you understand where that came from? We got 4 1/4 when it came back up, minus 2 when it went underneath. 4 1/4 minus 2 is 2 1/4. 2.25 is probably how they want it, but we just, you don't know what that means. It's the same thing. The main thing I wanted to get for you here, though, is that you can depress, if you know one of the 0s, you put in the box, and you can depress it to a quadratic in this case, and then you either quadratic formula, which will give you the right answers, or you can use the other clear 0 and depress that quadratic to a linear and get your answer. The one that's obscure, the one that's weird, the 4 point something. It turned out to be 4.25. So this is what you're doing today. You are taking factors that they give you and deciding whether they are actually factors of the big polynomial or not. And it all depends on whether the remainder is 0 or not. The other thing you're doing is you are believing that it is a factor and depressing it to a place where you can handle it into a quadratic. Remembering that this is one of the factors. See, we have x minus 2 times this, but then we have to further factor that into those, and we end up with this, folks. This is what we really ended up with as far as the math goes. Not the roller coaster, but the math. This cubed polynomial is x minus 2 times x plus 1 times x minus 4 1/4. That's what we've discovered. That cubed polynomial factors into these 3 linears. But to answer the question, it was this one minus this one as 0s, so that we could figure out how long it was underground. But what we did with the synthetic division was to factor it. Think you can handle this? Okay. Those of you doing it on paper, here's the assignment. This is called section 44B. And it is 39 to 51, odd, 52 to 54, and 57 to 71, odd. Okay? All right. There's that idea, folks. See ya.